Okay, welcome everyone. Good morning. Today's session is basically the final communication dissemination session of an EU project we work on. I will introduce you to that project, also say a few words about the program today, and then we will start first with the junior scientists and then with the senior scientists. And they will show their results of the project. Just a bit of history. Basically, the partners involved in this project, they have quite some tradition on both thermochemical liquefaction and upgrading projects, but also on electrochemical conversion. Those are EU projects I know of, we have worked on. Those are mainly about pyrolysis, HDL, and then upgrading and co-processing into biofuels. The other ones are electrochemical projects related to lignin conversion, oxidants production, and so on. And at some point we came together and we discussed whether there is any possibility to merge those fields and basically look into electrochemical upgrading of bioliquids. And that's what this project is about. So basically we use industrially produced crude bioliquids, and we try to upgrade, stabilize, fractionate them using electrochemical methods. And in this project we worked a lot on electrode preparation. We worked on electrochemical systems that basically do this job. And then also we validated the upgraded bioliquids for co-processing by FCC and by hydrotreatment. So basically, just to go a bit more into detail, the project is about using pyrolysis liquids and black liquor as the crude bioliquids. Then we applied oxidative and reductive electrochemical processes to convert certain bioliquid fractions into intermediates that then can be used by a refinery together with their refinery streams. The focus in the lab was a lot on electrode screening, electrode optimization of the production methods. The testing itself was done in different labs using electrochemical cells of different sizes, and at the end at small pilot scale. As I just mentioned, the validation was mainly initially, can we mix or can we blend our stabilized products with certain refinery streams? How could those upgraded bioliquids be used in the refinery? And specifically, we focused on the FCC and the hydrotreatment for fuels production. And we also did quite some analysis and evaluation of whether those final products are actually suitable as fuels. If you deal with bioliquids, you have to do obviously a lot of analysis. So we struggled and used a lot of different techniques to get hold of the reactions of the products and the intermediates we have produced. If we sum up the project itself, it was basically two main objectives. The first one was not to go the way via the hydrogen and then the hydrotreatment, but really use electrons or electricity directly to store energy in the bioliquids, and doing this upgrading the bioliquids ideally at the site of production. The reactions we targeted, both for the black liquor and the pyrolysis liquids, were three. First one was depolymerization of the heavier lignitic fractions into monomers that had the suitable size for fuels production. Then the decarboxylation of acids, which are basically quite relevant components in pyrolysis liquids. And then the third one was to reduce carbonyls, ketones, aldehydes into alcohols and polyols. And those topics are basically now the first topic of our session. So we start with our PhD students that have worked in the project. The first presenter will be Talal. He is a PhD student still at Twente University. He will very soon hand in his thesis. He has mainly worked on the decarboxylation of organic acids in order to fractionate and to improve the properties of pyrolysis liquids. And we look forward to this presentation in just a few minutes. Then we will continue with the lignin depolymerization and using black liquor. And the third presentation is done by Liz, focusing on the upgrading, mainly on the reduction of carbonyl groups into polyols. Then we will have a small coffee break, and after the break we will continue with the let's say senior researchers, PIs, and there we will basically go through the value chain of the project. We will start with black liquor and pulp mill integration of electrochemical processes. Then we will move towards the pyrolysis and integration of electrochemical processes in the pyrolysis value chain. Then we focus even more on electrochemistry, and then finally the use or possibilities for using bioliquids in refinery streams done by Sela. Yes, so I think we are known to overstretch our presentation, so I think we just start with Talal, and that gives us a bit of flexibility. So please come to the stage, Talal, and I will switch the presentation. If I find the mouse. Oops. I'm just not able to find the. Do you guys? Oh, there it is. Okay. Then we have to. Yes, there we are. Right. Okay, Talal, the floor is yours. That one works actually.
For the introduction. So I'm Talal, and I'm doing PhD at University of Twente with Professor Kihlman. So today I will talk about electrochemical decarboxylation of carboxylic acids on boron-doped diamond electrodes for pyrolysis oil application. And why we are doing this? So pyrolysis oil, which is obtained by this decomposition of the wood, it has carboxylic acids present, which are making it unstable and corrosive, and also the pH of the oil is very high. So our goal was to reduce, oxidize electrochemically these acids. But industrially, the pyrolysis oil can do, the hydrogenation was done on pyrolysis oil at high temperatures and pressures to make a stabilized pyrolysis oil. But electrochemically, this reaction can be done at the room temperature. So for those who doesn't have experience about electrochemistry, so I will show. So this is like an electrolyzer. Here you have cathode and anode, and the idea was to hydrogenate cathodically pyrolysis oil, and then because we need to have another reaction at the cathodic side where we will get proton source, which will be used for the hydrogenation of pyrolysis oil. So we decided to oxidize carboxylic acids present in the oil. And when we oxidize carboxylic acid, we can also form alcohols, which could also be blended into pyrolysis oil. The good thing with this electrochemistry is that you can store green electrons from renewable energy and to drive this reaction. So electrochemical decarboxylation occurs on, it's very subjective to the electrode material. Electrochemistry is mostly about the electrode material. So the reaction is in competition with oxygen evolution reaction. So here we see the reaction. It first starts with this oxygen evolution, and by changing the reaction condition, we can change the selectivity of the reaction. The decarboxylation occurs at high potentials, and when we use the different electrode materials, we have different product distribution. For example, when we use platinum electrode, we have Kolbe oxidation, where we produce a coupling product, which is ethane for acetic acid decarboxylation. But when we use graphite, we have Hoffer-Moist reaction, where we have formation of methanol and methyl acetate. But when we use other materials such as nickel foam and FTO, fluorine tin oxide, then we have selectivity towards oxygen evolution reaction. So this shows that this electrochemistry is most about the electrode material, that you can change the electrode material and you can tune the selectivity of your reaction. But the problem with the platinum is that it's a noble metal, and at high potentials, all these electrode materials, they go for dissolution. So we were looking for an alternative material which can be used at high oxidation potential and doesn't go for dissolution, and we can do decarboxylation. So in search for electrode materials, our consortium, they look for an electrode material called boron-doped diamond electrode. Diamond itself is an insulator, but it has been doped by boron. So boron is introduced in the diamond lattice, which makes it a semiconductor electrode. The benefits of diamond is that here we see this operational window. Then if we compare that diamond with the glassy carbon or platinum or gold electrode, we have higher potential window, which shows that the diamond can be used for any reactions which it lies in this region, and it's very stable. Because we have our decarboxylation reaction is in competition with oxygen evolution reaction, so we need to have a material where we don't do oxygen evolution reaction. But when we use diamond electrode, we see that the overpotential for oxygen evolution is very high, and instead of oxygen evolution, it produces OH radicals. And the conduction of, so this electrode itself is a very versatile material that you can change the doping, and then you can have different conduction level, and you can even achieve conduction similar to metallic electrodes. So first we did is the decarboxylation of acetic acid present. So we took acetic acid as a model compound, and here you see this three electrode cell, where we have working electrode, which was boron-doped diamond, counter, reference electrode, and then we were producing gaseous products, which were analyzed in situ, and the liquid products were collected at the end of the reaction. So the reaction mechanism here, it's quite different compared to platinum, because on platinum we have surface mediated reaction, where carboxylate adsorb on the surface, and we have the methane product for ethane product for acetic acid. But in boron-doped diamond, because of its inertness, we have hydroxyl radical production, and all this reaction is driven by hydroxyl radical. So it reacts with this acetic acid, forming acetate radical, which disintegrates into methyl radical, and methyl radical reacts with the OH radical and can form methanol. And if we have excess of methyl radical, then they can also combine and they can form ethane. And here in electrochemistry, we represent our results in Faraday efficiency, which shows that how much percentage of electrons are going to drive our desired specific reaction. And for us, it's the formation of methanol and methyl acetate. And we see that by increasing the current density, the Faraday efficiency increases. But when we have low concentration of acetate, we do see we have more selectivity towards methanol formation. But when we have higher concentrate of acid, we increase the selectivity towards methyl acetate as well. But at the pH, we don't see there is a much effect isn't much effect of the pH on the decarboxylation reaction. And then we switch to the propionic acid decarboxylation. And what we have found that when we apply the potential on the electrode in the presence of propionic acid, we don't have any direct oxidation, which shows that the propionic acid also oxidizes indirectly by hydroxyl radical. So what happens is that propionates oxidize with OH radical and can form propionate radical, which disintegrates, forming ethyl radical and CO2. Ethyl radical reacts with the OH radicals and can form ethanol, or ethyl radical reacts with the propionate radical and can form ethylene and propionic acid. So by applying different conditions, what we see here when we have propionic acid, so we have this formation of ethanol and ethylene, and the reaction is more selective towards ethylene and towards ethanol and then ethylene. But then we also see that we have product which is acetaldehyde. Acetaldehyde is actually formed by oxidation of ethanol by hydroxyl radical. So by increasing the current density, we do see that we lose Faradic efficiency, which shows that either some side reactions are occurring or some of our products is oxidizing. So that's why we couldn't close the electron balance. And then we increase the complexity of the mixture. So if we have the mixture of acetic and propionic acid with the same concentration, 0.5 molar each, and by increasing the current density, we do see the same trend that the Faradic efficiency decreases. But here, if we look at the product distribution, we have more Faradic efficiency towards propionate oxidation compared to acetate oxidation, which means that because this reaction is not surface absorbed reaction, it's OH mediated. So it means that OH radicals, they are oxidizing propionate compared to acetate. And then we use a model from the literature, and then we saw that, so we use OH as an scavenging agent for the acid oxidation. And then we saw that the rate constant of propionate with OH radical is higher compared to acetate. And here you can see that, so this is from the mathematical model, which shows that in the presence of acetate, we have more OH radical concentration present. In case of propionate, we have less OH radical concentration present, which means that in case of propionate, OH radicals, they are scavenged by propionic acid. But in this situation, this scavenging is less, which is also proved by these experimental results. So if someone asked me that, okay, you have acetate and propionate mixture, and then you want to preferably oxidize acetate, and how could you do that on BDD? It's not possible because it's an indirect oxidation reaction, and it's mediated by OH radical. So it all depends on the rate constant of the OH radical with that specific acid. So then we increased the complexity, so we added acidic, propionic, and formic acid. Formic acid oxidized by OH radicals directly to CO2. Acetic acid oxidized to methane, ethane, methanol, methyl acetate, and propionate oxidized to ethylene, ethanol, ethyl propionate, and acetaldehyde. And then we observed the same thing, that the Faradic efficiency start to decrease by increasing the current densities, which means that we have the possibility of over-oxidation of some of our products. But we still see the same trend that most of these OH radicals, they are going for propionate products, propionate oxidation. That's why we have higher efficiency towards propionate oxidation products. So yeah, it shows that even if you increase the complexity, the OH radicals will preferably oxidize with whatever present in the mixture. So then we were looking for the strategies that if we can avoid over-oxidation. So here you can see these are 4 electrolyzers, small scale in parallel. And if you look on that side, this is the general image, where we have, it's a divided cell, cathodic and anodic compartments are separated by membrane, and the electrolyte was continuously recirculating. So we tried to do these flow experiments, and then what we saw that so we choose propionic acid because in acetic acid we don't see much of over-oxidation, but in propionic acid we do see. So we choose the propionic acid oxidation in the flow configuration. And then we have found that at the low flow rate, at 10 milliamps per square centimeter, we do see a very high Faradic efficiency towards acetaldehyde, which means that our ethanol, which is the product, is oxidizing. But when we increase the flow rate, we do see this over-oxidation is actually avoided. This is actually because of the residence time in the electrolyzer. Then we did the flow simulation, and what we have found that if we have the low flow rate and high flow rate, in the low flow rate we have more eddies, we have more intermixing, and the residence time is higher compared to high flow rate. This actually avoided the over-oxidation. And then we tried to do mixed acid oxidation in the flow cell. So adding all the acids and then do the same oxidation. And then what we have found that at high Faradic efficiency, we compared to the batch cell, we have 10 to 15% enhancement, which shows that the flow configuration can avoid over-oxidation. And there is another way which we also did is by using the pulse electrolysis. Because the goal here is to control the OH radicals production. And if you control that, then you can avoid over-oxidation. So what we did, or we are still doing, is that so instead of going from like flat surface, we have developed in collaboration with Gondius company from our consortium, these diamond electrode pillars. It's a 3D structure electrodes to enhance mass transfer. And then we also tried different cell configuration. The work I showed was done in the small cell, which has the active electrode area 3.18 square centimeter. Then we also did the same experiments in the zero gap cell, and then we could reduce the cell voltage up from like 1.2 volts compared to the small cell. And then we are also doing the same reaction in the large cell to enhance the production rate. So what else is needed? Because now we got decarboxylation, but the problem with decarboxylation, it occurs at high potential. And then the cell potential is also very high when we do this paired electrolysis. So we need to find some other reaction which can occur at low potential so we can reduce the cell voltage. So if I give you an example that doing this electrooxidation of carboxylic acid at 100 milliamps per square centimeter, the cell voltage is around 8 volts, which is quite very high. So we need to look for some other alternative reactions that can be done at low overpotential, and we will get the source of protons. And then we also need to compare that, okay, if we hydrogenate pyrolysis oil in situ, what's the efficiency? Or if we just do the water electrolysis and have hydrogen evolution at the cathode and use that hydrogen for hydrogenation of the bio-oil. So we still need to work in that. So in summary, acetic acid, it oxidizes by OH radicals to methanol, ethanol, and propionic acid oxidized to ethylene and ethanol. But the Faradic efficiency is very high, and in the batch cell, we have less Faradic efficiency at high carbon densities, but in the flow cell, we can avoid over-oxidation. And so we still need to work more into how we can avoid this over-oxidation, and if we want to make this reaction selective, then we also need to work into electrode engineering by depositing some metallic nanoparticles which are selective to specific reaction. So in the end, I would like to thank our consortium and EU for funding this project, and my students, Timo and Victoria. And if you have any question, feel free to ask. And this is the QR code for our EBIO project, and you can have more information.
Thank you, Talal. Any questions?
Yes.
Thanks for this nice talk. The zero gap arrangement, how do you do this with BDD?
Yeah, so we got a BDD mesh.
Okay.
So, so it's a very thin mesh, and then you can press this BDD mesh with the membrane on both sides, and then you can have, it's not zero gap, but it is what we call a zero gap. The distance between the electrode is like 0.5 mm. But in the small cell, we have 4 mm of the distance between electrode.
BDD is known to corrode with methyl radicals.
Yes.
Is this also an issue here?
Yes, this is also an issue here. So we produce CO2 as well, which is coming from BDD degradation. But we have done prolonged experiments, and we didn't lose Faraday efficiency. So it was working for like 100 hours. But still, to see the lifetime of BDD for doing this decarboxylation reaction, it is needed to be subjected for even longer time.
Any other questions?
Yes.
Hi, Talal. Very nice presentation. In your gas phase, you never mentioned any oxygen because
We don't produce oxygen.
so whatever you do, you always extract your protons and your electrons from your chemical compound.
Yeah, so we do the in situ gas analysis and we don't see oxygen, but sometimes we do see hydrogen peroxide, but because this reaction is a long, like a 1 hour experiment, and by the end of experiment, when you check, you get like 1 to 2% Faraday efficiency of hydrogen peroxide. So instead of oxygen, we get some hydrogen peroxide.
Do you see paracetic acid?
We didn't analyze that.
Because the people at Fraunhofer claim that they can make it by this way,
Okay.
and that the carboxylic radical reacts with the OH radical, and then you're there.
Yeah.
already. And after hydrolysis, you would get hydrogen peroxide.
Yeah, we didn't analyze the for the acid per acetate.
Any other questions? No. If not, then we move on. Thank you, Talal.
Thank you.
Okay, our next presenter is Niclas Schupp from the Johannes Gutenberg University in Mainz. His focus was the electrochemical depolymerization of lignin in Kraft liquor, and he will present his results. Thank you.
Thank you. So I'm talking about the degradation of Kraft lignin and black liquor in that project. So first, let's start with the motivation. Of course, the core of EBIO is the treatment or the chemical upgrading of treated biomass into more stable and energy-rich bio-oils, and after further co-refining into transport fuels. And what's special about this project, or the uniqueness about the project, is that we're using electrochemistry for this kind of conversion. So that also means that we need some that we introduce some new parameters, electrochemical parameters, like the electrode materials. Okay, the electrode material. We have a different. We can play with the cell design, but we also introduce some electrochemical parameters we can optimize to maximize the yields or the outcome for our biofuels. So, but not only biofuels are here out maybe an interest. But electrochemical oxidative degradation of black liquor and lignin, you're also not getting some oligomers, which are potentially suitable for biofuels, but you also can get some value-added chemicals. These are mostly monoaromatics, and we can make them by electrochemical degradation of black liquor and lignin. So how to tackle that task? There are 2 ways to do that. The first is the so-called in-cell route. This is the most simple one, and it's quite easy. You're just directly applying current or electricity to the black liquor. This is what we did. Therefore, on the right corner there, we have special cells we made ourselves. These are high-temperature electrolysis cells, and for accurate solution of these black liquors, or the black liquor we used, we can go to temperatures above 100 degrees and still applying electricity to that. So, and before I started that, I did a so-called nitrobenzene oxidation. This is often taken as a 100% method to see how much of the vanillin you can get out in total of there. And for the black liquor we used, we can get 0.6 weight % according to the black liquor of vanillin. So we did some screening there, and this is what we found. We optimized some electrochemical parameters and ended up with 0.53 weight% of vanillin and also some acetovanillin. And the more interesting part here is that the 0.53 weight% are already 88% of what we can obtain in total. So this is one way to do that. The other one is the so-called XL route, and therefore we require an oxidizer. And we choose peroxidicarbonate to do that. This is an electrochemically generated oxidizer. You do before your treatment of the black liquor, you generate that and combine that afterwards. And this peroxidicarbonate, also called PODIC, the uniqueness here is that you can only do it electrochemically, but very good. It's a selective and non-harmful and also green synthesis. You're just applying to for example, sodium carbonate solution or sodium potassium carbonate solution current or electricity. Then you can generate your peroxidicarbonate. And this is already known for a long time, but there was not a lot of improvement for a long time. And you can see on the graph here or on the picture, it started with platinum electrodes, and after 2000 there were also BDD electrodes introduced, so boron-doped diamond, and after that there are way more publications, and also the concentration of the product increased, even up to 1 mole per liter, and this is where it's getting interesting, because by changing the concentration of these oxidizers, we also be able to get some new reactivities out of it. And this is just a small few of applications, what we can do with that. So we can treat a lot of smaller molecules with that, but what's always using a high concentrated peroxidicarbonate. But what's also interesting is you can do some bleaching of shellac with it, but also degradation of lignin. And this is what we did in our second route, the XL route. This is a 3-step protocol. So first we electrochemically generating the peroxidicarbonate. And if you're thinking in a maybe more in an industrial way or getting into there, you can also generate that on site on your plant. And you just have to store, for example, the sodium carbonate solution. It's way easier to store or transport hydrogen peroxide. So you generate that, then you mix that with your lignin in a caustic soda solution, for example, have some sort of pre-steering time. This is done at room temperature to pre-oxidize your lignin, and afterwards you have a heat treatment process where you really degrade your lignin structure, your polymer, into monomers and can get them out for further applications. And in theory, also thinking a bit bigger again, you also can use whatever you used, your sodium carbonate solution or your caustic soda solution. In theory, can reuse that also. So this is what we're also doing at the moment still. Yeah, and we're working on that. So that's my presentation. I want to thank especially EBIO for that, also the group and the whole consortium, and I'm open for questions.
Thank you, Niclas. Any questions from the audience? The PODIC, how easy is it basically the issue is always it's very reactive. That means it also degrades very fast, right? So it's ideally true, yeah. you would want to produce it more or less when you need it. Yeah, that's one thing. It's not very stable. It's stable at temperature under 5 degrees Celsius, but it doesn't take that much time to do it. You can also use high currents, so it's easily produced when you need it.
Okay. But at 5 degrees, you have a couple of hours.
Yeah, right.
The half-life at 23 degrees is 40 minutes or something like this?
Roughly 40 minutes, yeah.
Over 20 degrees, it's a little bit more unstable. But the good stuff is you just let it stand and then it's disappearing.
Right.
Evolution happens and then it's gone.
Okay. And is that more oxidative than hydrogen peroxide, or?
It has a completely different profile.
Okay. Any other questions?
Yeah, also in relation to this, the literature on peroxide synthesis, right?
Yeah.
Electrochemical synthesis by water oxidation finds that you need a very high concentration of carbonates, typically in the vicinity of the electrode. And then it also goes through a carbonate radical type of cycle. At least that's what people propose. So do you see hydrogen peroxide as well in your synthesis of the bicarbonate?
We did some IR measurements and NMR measurements. We compared hydrogen peroxide solution, also carbonated hydrogen peroxide solution with our product, and there we can clearly see that's not hydrogen peroxide.
Okay, so the product doesn't do this.
Yes.
Okay.
And most likely it's going to the surface, and the carbonate goes to the surface, it's oxidized, and it comes together. We also had the idea about OH radicals, but you need an oxygenated species which goes in the empty orbital there, otherwise it doesn't work. The important thing is, as you said, the carbonate solution has to be high. Unfortunately, most carbonates are not well soluble at cold temperatures. That means we have to use the inorganic trick. That means you have a dication, you need different cations. That's the Fehling trick that you use for tartrates, sodium and potassium, and it becomes very soluble. It's the same with phoscarbonates, that we mix the cations. And then you can make molar solutions, which is otherwise not possible.
The issue with our reaction, so what Talal explained, in the acid decarboxylation, you make CO2. If you have a very basic environment near the surface of the electrode, it dissolves, it forms carbonate. And we saw a huge effect on the selectivity, in particular for platinum electrodes, what will happen to acetic acid. So we completely switched the selectivity when you have carbonate in solution from the cold product, so ethane, to make methanol. And we don't fully understand this, so I think that there might be some reasoning in this particular chemistry that you are looking into as well. So we should discuss this, I think.
There are also some evidence that if it's more alkaline, the poly seems to be more stable as well.
Right.
Which indicates that a decay works via hydrolysis and then further. I think there's a lot of stuff still to be done.
Yeah,
I agree on that.
Yeah. Thanks, Niclas.
Just one more question. You have in the using the product, you have this 3-step process.
Yes.
And let's say the second step is you mix your product with your lignin, the soft lignin, and then you have the heat treatment. So do you know what happens actually during the mixing of the product and the lignin? Is it just activating certain groups, or?
Yes, something like that. It's not totally clear yet, but it's some sort of pre-oxidation step, so it's easier to do the heat treatment.
So you anyway, I mean, there's no chance to, let's say, not use the heat treatment. You need the heat treatment anyway. The moment, oxidative power is not enough to do it at low temperatures.
Just keep in mind, it's a relatively complex structure, and you oxidize it, and the aldehydes are still trapped in this structure. They're kind of acetals and other things, and by the heat treatment, you liberate. But then the oxidation is gone. That's I think the important point, that the oxidative event you separate from the liberation event.
Okay.
You will see this later on. Then if you do this systematically, the yields go really up.
Right. Okay, thank you, Niclas. Let's move on. Okay, so our final presentation of the PhD students is given by Liz. As I said, she's at the University of Mainz, Johannes Gutenberg University of Mainz, and she was focusing on the reductive part of the electrochemical cell, upgrading ketones, aldehydes into polyols.
Hope you can hear me now. Perfect. So thank you for the introduction, Roman. As mentioned before, I'm going to walk you through some results on the electrochemical upgrading of the pyrolysis oil, as well as some analysis that we did with the pyrolysis oil. So the shared goal that we all have and that we also share in EBIO is the development of an economical, environmental, and socially friendly process to produce transport fuels from biomass. And we do this by electrochemically upgrading low-value bioliquids like the pyrolysis oil and the black liquor. So Niclas already told you a lot about the black liquor, and my focus lies on the pyrolysis oil. And we want to achieve chemicals, platform chemicals, high-value compounds, or other compounds that you can use in biofuels. So as mentioned before, the focus on my project was the pyrolysis oil. This was supplied by BTG. You will hear a talk by Robbie, and he will go more into detail, but there are different fractions of the pyrolysis oil. There's a lignin fraction and a sugar fraction. These are the compounds that are more dissolvable in organic solvents, and the sugar fraction is more in water soluble. And there are different plans of action how to proceed with these fractions to gain compounds that can be used as biofuels. I'm going to focus on the pyrolysis oil itself and the sugar fraction. The analysis of the fractions were done mostly by SINTEF. They did different methods like LCMS and GCMS. We also established analytical methods like LCMS, NMR, and IR in Mainz University, and you will see some of that later. So first of all, here you can see the electrochemical conditions that have been used for the conversion of the pyrolysis oil. We used a divided setup. You can see the cells on the left-hand side. These are very easy to handle batch cells. They're divided, so you can use either a glass frit or a Nafion membrane. And as the cathode material, we use the BDD that was mentioned by Talal before. As the anode material, we use glassy carbon. So after the electrochemical treatment, you have the raw treated pyrolysis oil, which is then worked up. This is necessary because it's solved in methanolic sulfuric acid, so we need to neutralize the sulfuric acid. And then we have the treated pyrolysis oil, which was then analyzed by NMR or GCMS, for example. And in this analysis, we saw that the major carbonylic functionalities are successfully converted. We also did a very small current density screening, and we saw that higher current densities are beneficial for the conversion of the aldehydes and ketones. So the next step was the electrochemical reduction, but followed by a flow IR. So then we used the same cells that you saw before, but the pyrolysis oil is then pumped through a flow IR, and this is it's measuring an IR every 3 minutes. So we can observe the reaction over the chosen amount of time. And here you can see what this looks like. So this is a different IR spectrum. So over time, you can see how the reaction mixture is changing. You can see the different wavelengths that are specific for functional groups. And if you look at the color code, so moving from yellow over blue, green to this dark brown, you can see that there are some shifts in the typical wavelength. And this again showed the change in the carbonylic area. The identification and the quantification on the products itself is pending. There's another very interesting information in these flow ER measurements. So, for example, if we zoom in into the part into the specific wavelengths of carbonyl functionalities, we can normalize this to 100%, and then we can see the degradation over time. Not the degradation, the conversion over time. So starting from 100%, you can see that after a very short amount of time, most of the carbonylic functionalities are converted. Then if we move to the right-hand side, you can see that after a while there's still a little bit happening, and then there's nothing happening anymore. So with this information, we can estimate the amount, the necessary amount of applied charge that is necessary. So basically, how much electricity do we need for the conversion of these carbonylic functionalities? In this case, it's 1.7 coulomb per milligram of pyrolysis oil that is used in the reaction. The smaller part of the project was the conversion of sugars. This is very important if we move to the sugar fraction of the pyrolysis oil. So we heard in a few talks yesterday that especially the aldehydes and ketones can do a lot of polymerization in the bioliquids. So in this case, we have the cellulose that can be converted to the levoglucosan in the pyrolysis oil. The next step, the hydrolysis, is a very known process in literature. And then it's very interesting to see if we can maybe get sorbitol from the glucose. And we can do this electrochemically. But the first step for this project was, again, to check which analytical method is the most suitable for this case. On the right-hand side, you can see a carbon NMR spectra, and you can clearly distinguish between the levoglucosan, the glucose, and the sorbitol. But this is more for qualitative analysis. For the quantitative analysis, we used SEMS, and this was done in cooperation with SINTEF. On this slide, you can see the electrochemical reduction of the glucose, the reaction conditions to move towards sorbitol. As mentioned before, you can see the quantitative analysis with the carbon NMR. You can see if there's sorbitol after the reaction or not. And we investigated different electrolyte systems as well as different cathode materials. Over here, you can see the results on the chosen electrolytes. So you get 12% of sorbitol. The limitation in this reaction is either unconverted glucose or the rearrangement towards fructose. So glucose is more like in the ring structure, then it can rearrange, so with the ring opening towards fructose, and this is limiting the reaction. The next step in the project would be then to transfer these reaction conditions from the model compound towards the sugar fraction of the pyrolysis oil. As you can see in the NMR on the right-hand side, there are not only sugars in the sugar fraction. There are still some carboxylic acids and other carbonyl aldehydes, ketones, and a few phenols. So this makes it a little bit more challenging, especially with the analytics. And with that, I would like to finish my talk by thanking, first of all, Ziggy and the whole group that we have in Mainz and Mülheim now. If you're interested in electrochemistry, please check out our website. And I would also like to thank the whole EBIO team. We've been working on this project for 4 years now. So thank you very much, and thanks to you for your attention.
Can you put up the IR spectrum once more? So
This one?
Yeah, the peaks that disappear.
Yeah.
I think what is very important to note is also in infrared spectroscopy the things you don't see, right?
Yes.
And I think what is very interesting is, of course, you could also, if you have C double bond C compounds, you could also hydrogenate the double bonds.
Yeah.
But I think that would give a signal at around 1600, 1640, something in that range.
Yeah.
Which you don't observe.
No.
So is the conclusion indeed that you are very selective towards the hydrogenation of the carbonyls in aldehydes or ketones, and not so selective in the C double bond C hydrogenation? And do you have additional evidence for this? That,
I think it would also only be from the IR. Of course, we could specifically look into certain compounds that have a double bond and check in the GCMS if this specific compound is still there after the electrolysis. But from this data, it does not seem so. this could be changed. I mean, this comes into your field a little bit more, but we can change that by changing the electrode material, for example. So
this was done
with BDD.
with BDD.
Yeah, so we can change that.
So this is also a utilization of BDD for a reductive
Yes, yes, yeah.
use as a cathode.
Yes.
Yeah. Okay, thanks.
BDD is known to be quite expensive. What else could work? What electrode materials?
So I tested a few. For reduction, lead is used a lot. If we don't want to use lead, out of the obvious reason, we can use leaded bronze. And this would also work. I also tested it.
Any other questions? If not, then we have an extended coffee break, and hope to see you all back at 10:30. Okay, let's move on. We are now in the second part of the program. I will give a small introduction about the value chain of the project, but also about the industrial value chain we actually anticipate. And then the experts take over. We start then with Jonas from AFRY about integration of electrochemical lignin conversion in a pulp mill. Then we move on with the pyrolysis plant and electrochemistry, even more electrochemistry, and then we focus on the co-processing and the refinery requirements for fuels production. So just a small introduction about EBIO. So the value chain was basically to move from the feedstock to the biofuels, and moving along this value chain, we had a quite big focus on this electrochemical stabilization part. So we worked on the fundamental aspects, electrode screening, electrode testing, kinetics, and so on. And then based on that, we developed some small pilot scale TRL4 type of systems, and produced certain amounts of those stabilized bioliquids. In terms of the let's say lab scale fundamental studies, we more or less from the beginning used those small cells. We actually didn't use those typical beaker type of experiments, or we limited that as much as we could, starting with those cells, because that made then the scale up much easier, using more or less the same production line products, but just going up in electrode surface area. We also developed some lab scale test systems to do electrochemistry, but also to produce this PODIC, this electrolyzer that Niclas was talking about. And those small-scale lab electrolyzers, they can actually be purchased and tested out. We worked on different electrode materials, but also on electrode configurations in order to improve mass transfer, stability, and so on, and looked into ways of improving the industrial production of those electrodes. When it comes to the integration into pulp mills, that will be the topic of the next talk. But we basically initially the idea for the black liquor cycle was to take part of the black liquor and run it through a cell, and then have some separation, either integrated already with the Talal soaps or separate, and then whatever is not converted, we feed back into the liquor cycle. That we will also discuss in Jonas' presentation a bit more in detail. Basically, we had to come up with different options for that, depending on the electrochemical process we wanted to use. We also looked into some sustainability and societal impact analysis studies, And for that, we used the example case of Inlandet. That's a region in Norway which is very rich in biomass. It used to provide this biomass to the Norwegian pulp mills, but most of them are closed down. So today there's still some timber production, but a lot of the residues are actually shipped over the border to Sweden. And there's a lot of initiative and eagerness to re-establish some industrial activity in that region and use those residues basically on site instead of just sending them abroad. And there we did a lot of discussions with the communes, with the industrial stakeholders and so on, and came up basically with some case of establishing such a unit there. If we think about the value chain of the industrial process itself, it's very simple. Liquefaction, stabilization, upgrading, co-processing, and that's really based on what is available at this stage. In terms of liquefaction technologies, you have the Kraft pulp mills, you have quite some pyrolysis units in operation, and you have also the refineries that will need to use a certain amount of their feedstock coming from bio-based sources. And basically the whole point of this project is to work in this area which is linking the liquefaction and the co-processing. And there, as I said earlier, the goal for the electrochemical part was really not to produce a fuel in such an electrochemical cell, but really to stabilize the products in terms of long-term stability, in terms of distillability, in terms of energy content, but also to make the fractionation and the further handling easier. As I also mentioned already a few times, the feedstocks were pyrolysis liquid and black liquor, basically because this is what is available industrially and commercially. And the target was, for this specific project, it was fuels, but I mean, if you produce fuels, that always goes hand in hand with some chemicals production, but that was not really the target of the call and the project itself. But we get some hints what can be used, what can be valorized, and well, let's see how we can move on with this. So the first presentation now will be given by Jonas Kihlman from AFRY. AFRY was or is the partner that is responsible for the integration, process design of those electrochemical processes into pulp mills, and he will present those data and those options that are in principle possible for such an integrated electrochemical process. So let me bring up his presentation and
yes, yeah. So yeah, thank you, Roman. My name is Jonas Kihlman. I work at AFRY as a process engineer. Have been more or less this last 15 years working a lot with biorefinery concept, a lot of new technologies, very much connected to the forest industry. I have prepared this presentation today together with my colleague Carl-Johan. To wave to the audience. Yeah, great. So I will focus on electrochemistry as a method for lignin depolymerization for the use in the fuel application. You've heard about the background for the EBIO before here. But the aim in the 21st century will be to use as little fossil carbon as possible, and direct conversion of renewables is, of course, of continuously growing interest. And the application of electrochemical method for the synthesis of organic molecules is also have a revival during the last few decades. And the substitution of chemical redox reagents with electricity is a promising step towards green chemicals, green chemical processes. And this part of the slides will be very, very basic because me and Kalle, we are no electrochemists, so the ones that are expert, you could fall asleep for a couple of minutes, perhaps. But in any electrochemical process, electrons will flow from one chemical substance to another that is driven by an oxidation reduction, a so-called redox reaction. So a redox reaction occurs when electrodes are transferred from one substance that is being oxidized to one that is being reduced. And it is balanced when the number of electrons lost by the reductant equals the number of electrons gained by the oxidant. So like any balanced chemical equation, and in this case, the net charge is the same on the both sides of the equation. We have some example here. To the left, we have the galvanic cell that transforms energy released by spontaneous redox reactions into electrical energy. So the oxidative and reductive half reaction usually occurs in separate compartments that are connected by an external circuit. And you also have a second connection allowing ions to flow between the compartments, the dashed line showed on the picture to the left. And the potential difference, that is the voltage between the electrodes, causes electrons to flow from the reductant to the oxidant through this external circuit, therefore generating electrical current. On the other hand, to the right, we have the electrolytic cell, where we use an external source of electrical energy to generate this potential difference between the electrodes that forces the electrons to flow. And this is then driving a non-spontaneous redox reaction. So in the EBIO project, we have been looking at this electrolytic cell using electricity for driving a non-spontaneous redox reaction. Just some slide of water. I will come back to the function of water a bit later as well. But the water molecule here, I think it's blue or purple oxygen molecules and 2 red hydrogen molecules. And water is a strong dipole, so in a water solution, the water will come in contact with a negative ion, pointing its positive dipole towards the negative ion, and the vice versa for the positive ion. And when the positive ion reaches the negative ion reaches the positive cathode, in this case, the water molecule will give away, and there will be a potential difference between the positive cathode and the negative ion, and this will also break the bonds within the ion. So water, in any case with both negative and positive ions in the water solution, it will it will result in a charge neutrality, which is essential for a low electrical current flow through the electrolyte. So that was probably the most important thing that I will come back to later. But now, shifting focus to the bigger picture and also to the industry. So where do we want to do our electrochemistry? Lignin is available at the pulp mills, mainly in the recovery boiler, and mainly in the black liquor. And the black liquor is today used as a fuel in the recovery boiler, being burnt for generating heat and power for the pulp mill. And Kraft lignin is characterized by its inertness and degradation robustness, which complicates selective degradation. However, it has been shown in laboratories and also in some commercial processes that it is possible to break down lignin into valuable monomers, suitable, for example, for the fuel application. So in the EBIO project, we have taken an unconventional approach by applying electrochemistry to lignin, as it is available in black liquor in large volumes at the pulp mills. And coming back to the previous slide, black liquor is actually also an excellent electrolyte containing water, ions, and lignin, which is more all you need. And water is also crucial for a crucial reactant necessary for splitting the lignin into monomers. So water and lignin will react, generating monomers and an oxygen. And black liquor can be side stream and refeed at various positions at the pulp mill, between the digester to the right and the recovery boiler to the left. So in this area, the black liquor is thickened by evaporating water in different stages throughout the evaporation plant, and also black tall oil soap is also being skimmed off. And different thicknesses of the black liquor to be electrochemically treated have been tested in the project, and a fairly low concentration seems to be the most promising option, both in terms of the black liquor properties, the temperature, but also on the yield. So here is a very simple way of how we think this could be, our process could be integrated with the pulp mill. So we are directing part of the weak black liquor from the digester to the electrochemical processing unit. And after the electrochemical processing, the unconverted organic material together with the cooking salts could be returned to the black liquor cycle, to the evaporation plant. But before that, then we need to extract the desired conversion products from the black liquor. So separation of phenolic and short chain acid, which are the predominant production fraction, is either separated by a solvent extraction process, an adsorption process, or reverse osmosis. There have been extensive screening studies in the project of different separation options to be able to analyze the depolymerization products that we have received. So, and in conclusion, one of the first conclusions is that one of the most promising options includes a lignin precipitation step. So the pH is reduced by adding an acid, and the polymeric lignin will be precipitated, and the monomers will then be extracted by adding a polar solvent to the black liquor. So besides getting the electrocell product, you could also potentially generate some crude Kraft lignin. So this is very schematically shown in this picture. So how does our electrocell technology then stand in comparison to other technologies? There are different ways of looking at this. This is one way. And what we want to show here is the molecular weight transformation as molecules are broken down and changed to arrive at the requested size for the transportation fuel application. And this perspective is justified because any breaking or building of molecules is associated with some kind of energy requirement, making it a measure of energy loss. On the molecular weight scale to the left, we have at the top we have the largest molecules, and at the bottom we have the smallest one. And the first case is gasification, where you start from biomass. You gasify the biomass, generating a syngas consisting of carbon monoxide and hydrogen molecules, and these molecules are then built to generating the molecules for the transportation fuel size. So in this route, there is a lot of molecule bonds that have to be broken, so generating a relatively large amount of energy loss throughout this process. The second example here is a variant of the gasification, where we more or less take a shortcut and starting from black liquor. So the first degradation from the woody biomass to the black liquor has already been done at the pulp mill by the pulp mill's regular business. The second one is a pyrolysis of biomass, generating a pyrolysis oil, which more or less has this required size for transportation fuel. And to the right, we have the electrochemistry route, which seems to be the shortest one, as we are starting from black liquor in this case. This is a fairly short route, but this is just showing the transport molecule size in comparison to the desired size for the transportation fuel. So in both the pyrolysis and the electrochemistry route would need additional catalytic step to really produce molecules of the right quality for the transportation. So right or wrong, but this is one way of looking at it. So what is driving this development then? So lignin is a highly branched and irregular polymer, as we have already heard before, but it's one of the most abundant natural polymers on Earth. It's second only to cellulose. And new findings within the electrochemistry can open new possibilities to cracking the lignin molecule. And as mentioned before, the black liquor is an excellent electrolyte. The operational windows also for the electrocells fits very well to the pulp mill. We have moderate temperature and pressures. And also, as mentioned before, the unconverted lignin plus the salts can easily also be returned back to the evaporation, to the recovery boiler, recovery cycle in the evaporation plant. And this method could also be used for debottlenecking the recovery boiler. More or less every pulp and paper mill continuously tries to increase their capacity. And by doing that, the recovery boiler often becomes the limiting factor, because it's quite expensive to do investments in the recovery boiler. And by extracting part of the lignin from the black liquor, you could offload the recovery boiler and therefore increase the pulp production. And of course, valorization of additional products as chemicals and materials is a driving force behind this as well, generating new potential income for the pulp mills. And the electrochemical black liquor conversion unit is also expected to be fairly easily integratable with the pulp mill's existing recovery plant. And the electrocells are favorably multiplied and stacked to production units that could be adapted to the specific design capacity and also the specific mill requirements. And it could potentially become a competitor to alternatives like black liquor gasification or lignin extraction via acid precipitation. So what we have accomplished then, so the EBIO project has shown that electrochemistry can turn complex biomolecules into monomers. And electrochemical breakdown of lignin is proven in the EBIO laboratories, where we have C7 to C10 molecules successfully extracted. And the lab work setup allowed for studying inflow reaction by dedicated cell designs and also electrode configurations. And here we, for example, found that the voltage gives the specific chemistry and the current is the rate of the reaction. And as heard of before, different electrode materials has also been tested, trying to optimize the process. Of course, there are challenges, it's as in any most similar, I assume at least, chemical research work. For example, we face problems with selectivity, electrochemical selectivity versus side products, hydrogen production, oxygen production, and also a bit about over-oxidation we heard of before as well, over-oxidation to carbon dioxide, which is unfavorable. Electron degradation is something else we have struggled a bit with, and also deposit formation. And also the efficiency is of course important, and trying to optimize it to get for the full economy of the process, reducing the power input and so on. And also the product separation from the black liquor stream is also crucial, I think, for this process to have a separation process that is it's non-complex, it's efficient, and have a low impact on the pulp mill's existing operation. I think that's probably one of the key to solve here, to get able to integrate this type of plant into the pulp mill. So is electrochemistry the future, the key to the future use of lignin? So in the EBIO, we have focused on monomers for transportation fuels. We have seen some interesting and promising results. Breaking down of the lignin polymer by electrochemistry also opens up for production of other chemicals that we have not reached out for in the EBIO project. But these two things together, and in that perspective, we can say that electrochemistry may for sure be a key, or at least one potential key for the future use of lignin. So that was all from me. So thank you, the EBIO team. And any question?
Thank you, Jonas. Any first applause to Jonas, of course. Any questions from your side? Let me start. How much lignin could be used from a Kraft mill?
Yeah, quite a lot, depending on the recovery boiler, and you have some rule of thumb for how much lignin you could extract from the black liquor before it affects the recovery boiler too much and the temperature inside the recovery boiler. But you could say up to 30% of the lignin in the black liquor could be extracted. If you want to extract more, then you need to have additional actions inside the recovery boiler, I think.
And is there any options for using all of the lignin?
No, I think that would probably be quite complicated for the recovery of the cooking chemicals and the recovery boiler operation. If you are going to recover all of the lignin, that would be a challenge, I think.
Okay. Any questions? Yes, please.
How much yield and conversion are you able to achieve? So if you have 100% lignin you put in, how many depolymerization?
Yeah, you could adjust the amount of black liquor. Of course, it's a large black liquor flow in total, so you could range it. But correct me if I'm wrong, Roma, but I think we are, is it about 60% yield or something like that? We are.
Yeah, the challenge is if you want to get those aromatic monomers, then you have to stop at some point, because while you produce those monomers, you convert them further to smaller acids into CO2. So that's your bottleneck, and then you would stop at around 30, 40, 50% of conversion. Yeah.
So you're saying that 40, 50, 60% of the original lignin is actually down to monomers?
Yes, yes. That's what you can achieve. But then, let's put it like this. Let's say you have a conversion of 100%. Then your monomers will be something like 40, 50%, and the remaining will be smaller acids and also some CO2. Yeah. So if you want to have high selectivity, then obviously you have to go to lower conversions.
Yeah, usually you will end up maximum 10 to 15% for high selective conversions. Depends a little bit on lignin, but the ones which give higher yield are usually the more expensive ones. Therefore, you have to make a process that the rest goes back into the boiler. But if you go 40%, it's a white mixture, what we call in German exploded pharmacy.
Right. Any other questions? If not, then we move on with the next. There's one. Sorry.
The ring opening synthesis, does that require an additional setup, or are you doing that in situ as well?
That happens in a way as a consecutive reaction. Yes. Yeah. Okay, then thanks, Jonas, and we move on with the next presentation given by Robbie and Guido. That will focus on the electrochemical conversion of pyrolysis liquids. So we will start with Robbie from BTG, who is one of the I can say, pioneers of the pyrolysis technology, and we have been together working for quite some years on the catalytic and electrochemical upgrading of those pyrolysis liquids.
No, we're not singing now. We tried, but we didn't get the right tone.
Thank you very much for showing up anyhow at this EBIO conference. I tried to make your life a bit more enthusiastic this morning. I will start talking about pyrolysis and to refer to the exploded pharmaceuticals.
Stay here. Close the camera.
Literally what we are doing is not pharmaceuticals. It is fuels. And what we basically do, I'm not so much interested yet into chemicals, into pharmaceutical chemicals. I'm interested in changing characteristics of my overall liquids I'm producing. Where I'm from a company called BTG Biomass Technology Group. I think one of my colleagues gave a presentation in this audience 2 or 4 years ago in Finland, I think. And he explained what we are doing with respect to pyrolysis. Pyrolysis for us, it's a technique how to solve logistics. So how can we convert biomass, and especially the nice biomass resources we see here in Sweden, and solve logistics, and just by making it a liquid. Where do I come from? I come from the 1890s, the 80s and the 90s, where we started to work in pyrolysis at the University of Twente. So there is a direct link with the University of Twente. We took the concept from Twente to BTG, and then we explored and we commercialized the technology in Malaysia. And then we realized that we could do this better nearby on nice woods. Who am I? Well, I'm the one who was producing the first milliliters of oil at the University of Twente in the 80s, end of the 80s. I started to produce the first liters of oil for BTG in the 90s. I was there, but not responsible when the hundreds of liters were produced. And I was responsible for carrying out the task in Malaysia to produce tons. So I went from milliliters to tons, not because I'm brilliant, but simply because I was lucky. I was lucky to be there, and I believe in the concept. And after 25 years, or even longer, I still believe in it. And I believe that we solve logistics of biomass through pyrolysis. What we are doing right now is we have a company called BTL, and they are commercializing the technology further. They have 3 setups, 3 commercial units available in the world. 1 in Finland, 1 in Sweden, 1 in the Netherlands. And especially the one in Sweden is running very well. They are using the oils for co-refining in the Prem refinery. My dream in the past was to be responsible or be at least to be there when the commercial activities took place, to build my own pyrolysis unit. That's what I did in Malaysia. We didn't do very well, but enough to be confident to bring it to the Netherlands and to bring it 1 step further. My next dream was to bring this oil into a refinery. So I have ticked those boxes as well. My further dream is a concept my son already pointed at me in a couple of years. He said, why are we not using electricity and bring that directly in your oil? The boy was at that time 7 years old. So, and I think he's right. We can bring electricity into oil. What's the reasoning of pyrolysis? Well, simply, with pyrolysis, you are liquefying the biomass. It's not magic. We are cracking the molecules, and we are cracking cellulose, lignin, and hemicellulose. There are a lot of complaints about these bio-oils. It's smelly, it has oxygen, it's acidic, it's very reactive, but we solve logistics. Okay, we know the material is not as good as we want, but we know it's liquid, we can pump it. Literally, we can pump biomass, we can pump wood. To solve the problem of this oil, the problem a lot of companies might have with this oil, is first of all to produce a lot. So the availability. That's the box we have ticked. The next question is how can we make it better? So how can we make people aware of the fact that this oil is rather okay? So we have to understand a bit what the composition is. And you don't want to know. Actually, we don't know. So People think I'm an expert in pyrolysis. Actually, it's not true. I'm a one-eyed man in the land of the blind. There is no expert. Because this compound, the pyrolysis oil, contains roughly 200, 300, 400 oxygenated compounds. It's a diverse mixture of sugars, of lignins, of acids, aldehydes, and so on and so on. The problem people face with this oil is that they say it's oxygenated. I don't care about oxygen. It's about oxygen functionality. The other thing, it's a very high molecular weight. They are right. But we have a lot of materials which are low molecular weight. And so what is the real problem of pyrolysis oil? And then I have to show the characteristics is literally, and I pointed out here up front, first of all, it's an oxygen, but not the oxygen level, but it's the functionality of the oxygen. And no one is complaining to me around methanol. Methanol contains around 50% of oxygen. No one is complaining. So it's oxygen, the oxygen functionality. It's the high molecular weight, especially from the lignins. But as a matter of fact, I don't care that much about the high molecular weight, as long as these materials can be distilled. So what is my objective, if I want to make these oils better, is to get rid of some oxygen functionalities. And these oxygen functionalities are literally those of the cellulose, those of the sugars. So if I'm able to change the sugars into something better, then I'm able to go and bring this path forward to a refinery. Sugar chemistry is very, very well known. But what people do tend to forget is that our oil is not an oil. We made that mistake already in the 1980s when I wasn't there. Probably I would have made the same mistake. It's not an oil. An oil represents a material that is not soluble in water. Our oil is soluble in water. It's not an oil. It's a mixture, and it's the mixture of carbohydrates, a syrup, in which the lignin materials are emulsified. It's much better. So what do I have to do to attack and to make it better? First of all, to do the right thing at the right timing, at the right conditions. Those are the sugars. Sugars are very reactive. If I can change the sugars, I can do something better. And then I can change the lignins. Lignins are like oils. So what we did in our company is change this complete concept into sugar chemistry versus lignin chemistry versus a refinery. What I want to do up front is to look at the sugar chemistry. Now everyone knows that if I have sugars, I put it into a pan, I make caramel. Now typically 20% of the sugars are converted into caramel. This is what we call the MCRT, microcarbon residue test. It's a very simple method. And what really strikes me is that in literature, no one is addressing our pyrolysis oil in relation to the charring tendency, in relation to the MCRT. In our company, this MCRT is the most important parameter we are analyzing. And why is it that simple? Because it's just a distillation. We have an oil, we take a couple of grams, milligrams, we know up front how much it is, we distill the whole material, and we analyze how much is left there as a residue. 20% of our oil will be there as a residue. Typically glucose, if we take glucose in water, it has the same value. 20% of the material ends up in char. 20% of that char is around 40% of the carbon you had initially in your glucose molecule. I would like to reduce this one down to around 10. That's my objective. And then I can start and can do it further. So our process is like this. We separate the lignin chemistry, oil chemistry from sugar chemistry. And we do the right things first. Sugar chemistry, sugars are very reactive. They are hydrogenated very well at low temperatures, but high pressures. Then we take the material and we go to the deoxygenation. We do with different catalysis, different operating conditions, different processes. So what we basically do is try to get the pyrolysis oil, solve logistics, and now we are in a phase where we try to get this oil into a refinery to make it better, either through the stabilized oil or through the deoxygenated oil. What you saw yesterday from the people from Tupras, we gave them the deoxygenated oils, simply because they are already easy to handle. And this deoxygenated oil gives me very surprising results in many factors. So after 30 years, I still believe in the technology. Why electrochemistry? Well, electrochemistry, what people tend to forget and what people think is electrochemistry is easy. I take a battery, an AAA battery, I take 2 volts, and I'm able to dissociate water into hydrogen and oxygen. What people tend to forget is that this is the only technology existing where we can change, where we can transform water into hydrogen and oxygen. Literally, it's brute force. Brute force. If we can apply this technique on our oils, as my son said, put those electrodes in bio-oil and you make a better material and you store electricity, then we have something. We can do it at 20 degrees Celsius and 1 bar. Well, in the hydrodeoxygenation, in the stabilization, we need 200 bars. So for me, the challenge was there, okay, let's try. Let's try and fix and see where the problem will end up. My boss asked me, he said, well, Robbie, if the electricity is for free, what are you going to do with the pyrolysis oil? And literally I started to do research and found out 2 processes. One was very easy to find, which is the Kolbe process. And the other one was very difficult to find, which is the Kraton process. What I wanted to do is to get rid of the acids on basis of the literature, because I have acids in my oil. I wanted to produce the protons, produce the electrons, and use them for the hydrogenation. And the sugar chemistry on, let's say, the conversion of glucose to sorbitol was already done, I know, in the past, in the 1930s. Actually, I realized that everything we are doing has already been done before. Maybe not as good as we want, but everything we are doing has been done before. This Kolbe process is a very nice technique from the 1800s. A lot of information is available over there, especially on platinum and stuff like that. On the Kraton process, there was really a search to find the right literature information there. I found the information from the US. Literally from my report, Helena Kuhn from Seri in 1983. And she was having some sort of review on electrochemistry of biomass-derived compounds. And she has stolen my idea 40 years ago. Literally everything we are doing has been done before. I know Helena, so I had to apologize. And actually I asked her apologies, but she didn't give me. And she's right. What I want to do is literally using a fuel cell, taking the reduction on the cathode side, taking the oxidation on the other side. And what we are doing here is brute force. So we are not asking the pyrolysis oil to provide protons and electrons. No, we force them. And if they don't give it, we switch on the voltage. That's basically what we do. So on the right-hand side, I try to store my protons. On the left-hand side, I am stealing the protons and electrons from the molecules. And at the end of the day, I try to make something that is better than the original material. Then the question is always, what is better? Well, no one knows, so I can make my own definition. That's nice, because I always can tick off the box. The materials we used and the information, the equipment we used are summarized a bit here. It's on a NICA on the left-hand side, down to larger units we built later on. The ICA device, I have to pay some, I have to mention the people from Mainz. I think they are involved more or less in the development of this technology. Anyone in this audience, if you want to know anything about electrochemistry, get some hands-on experience, buy that thing. I'm not getting any, I don't have shares there. I don't profit from it, but that thing is the iPad under electrochemistry. So we use that one a lot. It's a very small device, potential state, electrochemical, CV, constant current experiments, whatever you can do, it's there. We then went into the smaller units, like fuel cells. We bought them from Horizon Fuel Cells. We opened it, we dismantled it, we destroyed everything there. Then we got the material from Condias. We got the material on the electrodes from Condias. And then we built a larger unit to play around with large volumes. Also with respect to electrodes, there's very small ones for ICA. For a divided cell, undivided cell, we went down into the cells from electrocell. I don't think they exist anymore. And now we are using the cell from Condias. And the nice thing about Condias is they also provide you with BDD. I am using technical feedstocks. And what I see is that I will destroy my electrodes. All electrodes, except one, the BDD. We tried to destroy the BDD for a long time, We are not able to destroy them unless we take some sort of a sledgehammer and we just kill them. That's it. So they work very well. What do we do? Well, apart from the cells, apart from the units, we can also play around with the configuration. So we started more or less the easy part. We fractionated the oils, we make the sugar phase, we make the lignin phase, and we start playing around with it. So on the left-hand side, you see here the lignins, and on the right-hand side, the sugars. So I take the sugar phase, I try to add protons, electrons to my sugar phase. And I can tell you it works. On the left-hand side, I have the lignins. What do I want to do with the lignins? I wanted initially to destroy my acetic acid, to get rid of it. What appears to be, and how beautiful nature is, because the nature is always tricking me, what nature does is destroying the lignins, is reducing the size, the molecular weight of the lignins. So instead of the acetic acid, the Kolbe, it starts to do the depolymerization, which is very nice. What is the consequence? And I was struck to see it, and for me, it means a lot. For you, probably less, but I try to explain. Is what we do, we start with, on the sugar phase, with a very black material. I don't have anything against black, but I know when it becomes transparent, I know I've done something very special. And this was for me the trick 20 years ago to start working on catalysis, and a very specific catalysis, where we were able to produce an oil which was transparent. I didn't do changing the molecule structure or the phase separation or whatever. No, it starts to become transparent. What I'm doing there, I'm destroying some compounds responsible for the color. For me, this is acetic acid, the aldehyde, the sugars, they are hydrogenated, but also the double bonds. So I am hydrogenating the double bonds, and I'm hydrogenating the aldehydes. It's more clear on the right-hand side. We did it in a very small experiment. And what is nice to see here is that if I take the carbon level in my sugar phase, I'm not destroying the carbon. I keep my carbon into my solution. And people who know me, I'm always focused on how much carbon will end up in my final products, because that's the essence. I don't care about hydrogen. It's about the carbon. I would like to end up with a lot of carbon in my final product. At the end of the day, preferably also in my fuels. So I know I'm hydrogenating the sugars. And this is clearer from this picture, where you see the time frame in coulomb per gram. So how much coulomb I have added to my molecules. And you see the hydrogen over carbon on the x-axis and the oxygen over carbon of the molecule on the y-axis. And you see that the oxygen level remains the same, but the hydrogen is increasing. So I'm hydrogenating molecules. I'm not destroying and getting rid of oxygen initially. What I do there is something special, because what I do there is I am reducing the aldehydes. What I don't want to do is produce hydrogen. The hydrogen is a loss for me in the first place. I can use it later in my process, but initially I don't want to produce too much hydrogen. I would like those electrons and protons to be connected to the molecules. So what you see here is, as a function of the time, the coulombs per gram I add to my molecules, the amount of hydrogen I produce. And what I did here is take the Faraday efficiency, which is 1 minus the electrons required for hydrogen production, as a function of the coulomb per gram. Now, the ones who were here in the previous presentation know the 1.7 coulomb per milligram you can use for full conversion. The same here is plotted on the x-axis, but then in coulombs per gram. The same order of magnitude. And the nice thing is, this corresponds, this 1,700, 2,000, corresponds to molecules like sugars that are converted into sorbitol and use a two-proton mechanism. For me, the most interesting picture is given here. We can measure the carbonyl content. And I know the carbonyl content is a measure for stability of the oil. And what I do when I add coulombs per grams is I simply reduce my carbonyls. And it goes through a straight line. And again, it ends up somewhere around this 1,700. And believe me, I didn't tell this in the previous presentation. about our 1700. But she got exactly the same value, 1.7 grams per milligram. If I would have told Liz, she would have used my definition, 1700 per grams, instead of grams per milligrams. So far, so good. But I have a problem. Because if I start to do my MCRT measurements, I still don't see too much things happening on the MCRT. It's not reducing. So I ended up with around 20 when I start, and I end up with 20 when I finish. And this is a problem I really didn't understand. Why is the MCRT still that high while I do a lot of things? One of the reasons is because the lignins are not very susceptible to be destroyed. Initially they might be, but what you can see at a certain time is stuff like this. You get deposits on your electrodes. And when you get deposits on your electrodes, the electrodes are not doing anything anymore. So your voltage increases, your milliamps are reduced, and you don't do anything anymore. So we had to redefine the concept a bit. So not the lignins on the one hand side, the sugars on the other side. We had to do it slightly different. So what we did is to change the concept a bit, dilute it a bit further. 20% of the lignins of the prolozol we are using in a direct concept, where we are oxidizing reduction, reducing the material. Then we do the recycle, and we try to generate materials in which the lignin is soluble on the reduction phase, on the reduction side, go to the oxidation and try to destroy the lignins. Bring it back to the reduction side, bring it back to the oxidation side, and do it for 100 hours. And what's the nice thing about this? It seems to be a very stupid concept, but we are not producing hydrogen, a limited amount of hydrogen, we are not producing oxygen. As a matter of fact, I believe that in a concept like this, we don't need the membrane anymore. I remember, and that's the link towards university, the first time I went to Guido, I asked a very stupid question. So stupid that Guido was not able to answer directly. I asked him, why do we need a membrane? And then he said, well, we have to separate the reduction and oxidation products. I'm not doing it here. It's a very simple concept. I have an electrode on the right-hand side, an electrode on the oxidation side. I do the oxidation, reduction, and so on. And I'm producing a very nice material. And again, what I see here is a reduction of my carbonyl as a function of time. And this is not a single experiment. I don't like single experiments. I like a lot of data. I like data mining. So we did a lot of experiments already here. And the comfort level for me right there is we are reducing the carbonyl. We are changing the colors of the prolozol. And now I have to find a concept around it. I still have one problem. I'm still not reducing my MCRT level. And the reasoning behind that is because I'm adding something to my prolozol at the beginning that will destroy my carbonyl, my MCRT level. I add something that is catalyzing the MCRT, catalyzing the polymerization. I now also know how to get rid of it. What you see here in this picture are a lot of data points, and the data points represent that composition. And what we are doing right now is going from the large circle over there, going back to the small circle there. We are changing the MCRT, going from 25, around 25, 30%, down to around 15 or 16. For me, that might be enough to put it on for a further deoxygenation step already. So there might be quite some possibilities here, and might be some possibilities here, that I can avoid the very high pressures of 200 bars. Future experiments should find out. But I was very optimistic about this. There are a lot of possibilities because I do it at 20 degrees Celsius, 1 bar. There are a lot of challenges ahead. I have to do a lot of steps. But the nice thing here is electrochemistry can be very cheap, very simple. Not if you start using platinum, iridium. But what we are using here is rather cheap material. Although we still have the BDD. Maybe we should change the BDD in a certain time. Next question. So the conclusions are there to say we are changing the carbonyl level. We are doing exactly what we want. The sugar chemistry. We are lowering the molecular weight. I didn't show you the figures right now. We are, let's see where we are. We are increasing the hydrogen content. So we are adding the protons and the electrons to the molecules. We are not producing a lot of hydrogen, so we do it very efficiently. We're not producing oxygen. So oxygen is the one that requires a lot of voltage. Voltage is a problem still, by the way. We are going to too high voltages, I have to say, simply because we didn't optimize yet. But we are able in reducing the MCRT as well. For me, when we started this approach, it was very uncertain where we would end up with. I knew a bit what we would like to have. So that was a step in the dark. And I'm really surprised to see how good this process works. Already, from our point of view, we didn't start with a lot of expertise on electrochemistry. So there's a lot of potential in electrochemistry. And I should be careful to say potential here in this audience. The concept is proven. We do it already on quite large scale. So we know what we're doing right now. We need a lot of analysis in front of us. We know where to look at, and it might well be a very nice add-on to the process we already have. Having said this, I would like to give the floor to Guido.
Now, yeah? Okay, so I just want to highlight a couple of things more on the fundamental aspects of the chemistry that we have been doing, or the electrochemistry that we have been doing over the past 4 years within EBIO. Me coming from a university, of course, I was addressing some of the, now he's holding the 3-minute bar, you know, so. Some of the more fundamental questions that Robbie approached me for and that we could really nicely study. So here's the cell concept once more, right, that we want to do reduction reactions on the cathode of an electrochemical cell, and we want to do oxidation reactions on the anode. And we took things a little bit apart. So this is the concept where both are happening in parallel, right? So this is treating the oil both in the cathode and the anode. We separated this. We looked at the cathode and the anode separately and tried to understand what chemical reactions actually take place. And of course, we also had to simplify the composition of the molecules, the molecular composition that we were trying to treat in the electrochemical cell. So the first, I think, highlight is this one, where we looked at acid decarboxylation, acetic acid. There was quite a little bit of literature already available, but the reaction mechanism and the effect of electrolyte composition was not so well known. So this is something that we started off with. What you see here, there's also a lot to say about the effect of pH in this reaction. But what you see here is basically that we varied the amount of electrons per time, the current density that we pumped into the cell or into the chemistry essentially. And what you then see very clearly is that if you are at low current densities, you create mostly oxygen. If you go to higher current densities, then you start seeing the reaction of the acetic acid. And the main product here is the coupling product of the methyl radicals that you form. So the mechanism is the acetate falls apart into CO2 and methyl radicals, and the methyl radicals combine to ethane. And that's essentially what you see. The blue bars are the ethane, right? But it is a strong function of the current density, as you can see. And on the left figure, this is something that we do in electrochemistry a lot, is record what we call cyclic or linear scanning voltammograms. And what we then do is we scan the potential and we measure the associated current at each potential. So we can vary the scan rate. But the important message here is that, very interestingly, what you see is if you take something that doesn't contain acetic acid, perchlorate in this case, this is a very common electrolyte if you want to study water oxidation type of reactions. And what you clearly see is that the current initiates at about 1.6 volts, and a lot of oxygen starts to be generated. That's the black line. And if you take acetic acid in solution, you suppress the oxygen evolution. Now, this is already the first indication that apparently the acetate is adsorbing on the platinum surface. This was for platinum electrodes, and is inhibiting the oxygen evolution reaction. And at the same time, this is also very nicely shown by this current density dependency where we produce the ethane from the acetic acid decomposition with very high Faradaic efficiency. Faradaic efficiency in electrochemistry is another term for selectivity that you would use in heterogeneous catalysis, let's say. So that's all very nice, but then what we also discovered was that if we go to very high pHs and we follow as a function of time the ethane productivity in the cell, you see that this slowly but surely declines, right? So the selectivity, the Faradaic efficiency decreases from about 80% to about 60%. And we were wondering, why is this? And what you see on the right is basically the equilibrium of CO2 in acidic or basic aqueous solutions. So CO2 dissolves in water and forms bicarbonate at sort of pHs around 8, and is deprotonated further to carbonate if you go to very basic pHs. Now, one of the products of acetic acid decarboxylation is CO2. We form CO2 near the surface of the electrode. This dissolves in the electrolyte and forms this bicarbonate or carbonate. Since we're consuming, since we are producing actually a lot of CO2, we can have this dissolution, and carbonate might be an interesting, effective agent for the selectivity. And here you see this once more. Now we purposely add carbonate to the electrolyte, and what you see is, and that's most evident from the right figure, is that if we add 0.1 molar or 0.5 molar, we completely switch the selectivity of the acid decarboxylation from ethane as the main product to methanol as the main product. And so when you form methyl radicals, they can do two things. They can react with each other to form ethane, or they can react with an hydroxyl radical that is also formed in the process. Methyl radical, hydroxyl radical forms methanol. And that's what you see here. So the take-home message here is that you can manipulate acid decarboxylation very strongly by manipulating the electrolyte composition. And in particular, carbonate has a very strong effect on this particular chemistry. So that's what I wanted to say about acid decarboxylation over platinum electrodes. Now, Talal already this morning gave a very nice presentation on what if we take different acids and different electrodes. And one of the highlights of his work is propionic acid decarboxylation using these BDD surfaces. And then probably we don't have surface-mediated chemistry, but we rather have all hydroxyl radical-mediated chemistry going on in the vicinity of the electrode surface. You see the different routes and different products that you can form. Essentially, the fingerprint of propionic acid decarboxylation holds the ratio of ethanol versus ethylene. And so by propionic acid decarboxylation, you can form either through the top route, you can form ethanol, and by the bottom route, you can form ethylene. And again, this is a kind of repetition of Talal's results, but what you can clearly see is that you get a mixture of both. So the top route and the bottom route in the acid decarboxylation of propionic acid gives you a mixture of ethylene and ethanol. And again, the Faradaic efficiency, we don't want to form oxygen, which is the competitive reaction, right? The water oxidation reaction. And you see that is really, really minimized. The other thing that you see in the cyclic voltammogram that is on the left is you don't have this sort of inflection zone that I showed you for platinum, which is an indication that surface-mediated reactions are probably not taking place. And hence, this was also the conclusion of Talal this morning, that this is all hydroxyl radical chemistry in the vicinity of the electrode surface, but not surface-mediated. And that the radical reaction rate, the kinetics of hydroxyl radicals reacting with either, with the propionate, apparently either towards the ethanol or ethylene, makes this selectivity ratio that you see and observe here. So the big difference and the take-home message is platinum is used when you want to have surface-mediated chemistry and very good at acetic acid decarboxylation. If you take BDD, this surface-mediated chemistry is much less significant, and this is all based and governed by hydroxyl-mediated reactions. Okay, then a little bit about the other side of the cell. So Robbie also came to me, he said, well, what is actually hydrogenated? If, say, we have species with CC double bond or carbonyl functionalities or aldehyde functionalities, what actually happens? First, to show you that, of course, we want to prevent the competitive hydrogen formation, as Robbie also explained. And you can do that by varying the concentration of the reactant. So here we took butanol as the model compound, if you like. And what you clearly see is that if the concentration of the butanol in solution is too low, you don't form much butanol, but mostly hydrogen, right? Up to selectivities of 80% towards hydrogen. So you need significant concentrations of the aldehyde to get this to be hydrogenated to the respective alcohol, right? 1-butanol in this case. And the other question that Robbie came to me with is, okay, if we take a double bond containing aldehyde, in this case it's crotyl aldehyde, can we hydrogenate this to, again, to the alcohol, the crotyl alcohol that you see there on the bottom, or is the double bond hydrogenated, which would yield you, again, butyraldehyde, right? Well, very interestingly, this is the selectivity distribution, the product distribution. A lot really goes to crotyl aldehyde. That's the red bar that you see here, right? More than 70% of the electrons that are flowing through the cell are used to produce basically the aldehyde conversion to the alcohol. So that's crotyl alcohol. There is a little bit of butanol, 18%, so there is a little bit of double bond hydrogenation, but there is a high selectivity, and this is for copper electrodes, towards the hydrogenation of the oxygen functionality. So hence my question also to Liz this morning, do you see hydrogenation of the double bond? She couldn't see that either, and that's in complete agreement, although the electrodes were very different for this particular electrode, copper electrode, and reaction conditions that we applied here. Then we were asking the next question. So what now if we take a mixture of a linear alkane aldehyde, so the butyraldehyde, and if we take this double bond containing aldehyde, is there what we would call a substrate specificity? So does one component react before the other? And so we took mixtures of these two aldehydes to see which of the two reaction paths is preferred over these copper surfaces. And that's basically what you see here. So the right bar now is the mixture, and you see that it's very similar to just crotyl aldehyde. So this shows you the surface specificity or the reaction selectivity on the basis of the two components is very selective towards the conversion of the double bond containing molecules. And the butyraldehyde in this case is hardly participating in the reaction. Of course, we wanted to understand why. Why is the crotyl aldehyde so much better converted over these copper surfaces than the alkane, the butanol? And so we looked with spectroscopy to differences in the surface adsorption. And here what you see is Raman spectra. I won't go into a lot of detail, but essentially what we see is that the aldehydes, they adsorb on the copper surfaces through something that we would call a carboxylate. So you have a carbon with two oxygens down onto the electrode surface, and that is the initial state of the adsorption. And if you look at this particular butyrate, that's the carboxylate bands that you see in the Raman spectra, they are completely different for the crotyl aldehyde, right? So here you see essentially very different spectral features, and that indicates that there is probably a somewhat different adsorption mode of the aldehyde and the corresponding alcohol as a product towards the copper surface through this particular double bond. So the double bond is a way also for the molecule to coordinate to the surface and be converted. And that adsorption probability is probably significantly higher than of the non-CC double bond containing molecules. So with that, I'm 10 minutes past time, I guess, but these are the take-home messages of what we have learned, more from the fundamental aspects of all the reactions that are relevant for Robbie and also for the paper mill and the black liquor conversion. On the one hand, we analyzed the decarboxylation reaction, and we saw that the electrolyte composition has a strong effect on the selectivity for platinum electrodes. Either you form methanol from acetic acid decomposition, or you form the ethane. I showed you that BDD is a different type of material, which has a different way of oxidative conversion, namely through hydroxyl radical mediated reactions. And finally, that there is also a lot to learn from the hydrogenation of aldehydes containing either double bonds or not. Aromatics, I didn't have time to talk about this, but this is also, of course, tuning the selectivity and substrate specificity in this particular case for copper electrodes. So with that, I'd like to thank you also for sticking around. And I think Robbie and I are happy to answer any questions that you might have. I also want to thank Roman and all, and Siggy and you know, the PhD students at Mainz for a very pleasant collaboration the past 4 years. I've learned a lot. I hope you have too. And yeah, again, now we're open for questions.
Thank you.
So Robbie, come back on stage.
So any questions?
If Roman allows us to answer any questions.
Yeah, it's okay.
Yeah.
The double bond with the carbonyl sample you have like on the picture.
The crotylaldehyde, yeah? Yeah.
So here, when you have without double bond and when you have with double bond, so with double bond you are getting like a better conversion because
Yeah.
the double bond probably the coordination with the upward surface.
Correct.
Because the double bond is in conjugation.
Yes.
And if you do like any example when double bond is not with the conjugation, you try with that kind of
No, we have not done that. But
prove exactly like
yeah.
because the double bond is in the conjugation.
Yeah, yeah. No, that's still an open question. But there is also a lot of literature in benzaldehyde hydrogenation over electrochemical surfaces, and they're looking at the interactions of the benzyl ring with these electrode surfaces, and that also gives very interesting differences in reactivity, you could say. Yeah.
Yeah, I can ask, since I know you work with catalysis of the pyrolysis oil as well to remove the sugar aldehydes, how does this compare? As I see it, you reduce the MCRT a bit to 15, still quite high. But, as I understand, is the win of this that you can use lower pressure in when you subsequently do some hydrogenation?
Yeah, the initial idea of EBIO was to try to get material that could be used as a fuel, because that was a quite high ambition level. What we have to realize is that we have to lower down the ambition level a bit, in the sense that you are going to stabilize the oil. With respect to stabilization, I think this technique is a very interesting technique to do the first step. You have to do a bit more, like hydrogenation, but it could be a very nice technique to do a bit more. And this is mainly on getting rid of the first problem you will have in pyrolysis oil, which is the sugar, the carbohydrates, basically the dehydrated carbohydrates. So I think, to be honest, and it's something I found out later in the project, as I mentioned before, this is an analogy with what we have been doing in the past. So sorbitol hydrogenation was invented somehow around the 1930s by Creighton, electrochemically. They built a pilot plant, they built a demo unit, they built a commercial unit, and then they found out that the hydrogenation over hydrogen and rainy nickel was cheaper. So they invented
even more electrochemistry. The next presenter is Siggy Waldvogel. He is still professor at Johannes Gutenberg University in Mainz, but he is also the director of the Max Planck Institute for Renewable Energy Conversion.
Can you hear me? maybe now better?
Yeah.
Yeah, okay. You see 3 icons here, and the one is, most of the work was done at Johannes Gutenberg University. I moved last year to Max Planck Institute for Chemical Energy Conversion, the place where honey and milk comes out of the wall. And I'm now affiliated to the KIT. That's a different university, but not so bad. Okay. I will talk a little bit about, in a general way, maybe put also some water into the wine. I will talk today a little bit about lignin. We worked also on turpentine fraction, but also tall oil to make thermosets and all the other stuff. But we fall in love with the underutilized feedstock stuff. And of course, there's lignin and there's also bark. I'm not talking too much about bark today, but this is our new focus, our major focus as well. But if you go to lignins, some people say it's a side stream which is not used, but just keep in mind, big mills say, okay, up to 50% they can take out of the system and still will operate. But the problem is, if you buy Kraft lignin, it doesn't come for free. It's about 500 euros for a dried up version. Lignosulfonate is almost double, and organosulf will be in cost scenario even higher. Therefore, this is the cheapest version you can get, and this should give you at least a baseline how much you can invest. We want to go for something like vanillin out of it, and then if you go look at Kraft lignin, there's one method which dates back to Freudenberg in the 1930s. That you treat it with caustic conditions with nitrobenzene, and then you end up with the maximum amount of vanillin coming out of it. The reduction of the nitrobenzene provides some really toxic byproducts, but which stabilizes the desired product. And this is nothing you can use, but only it's a gold standard how much you can take out of the lignin. This is the important part. Some general comments here as well, because we heard this yesterday as well. Just keep in mind, in Germany we switched off the nuclear power plants. We will stop the coal and gas firing in the future. We have mostly regenerative energy material, and that means it's usually wind power and photovoltaics, and the other ones are small numbers. We're now at 65% regenerative energy, and this will maybe next year almost 75–80%. And the question is, what can we do? The problem is that the demand doesn't fit to the supply. And then the question is, can we do a big battery? We are still a heavy industry country. That means just to bring it down on a certain level, BASF needs as much energy as whole Denmark. This gives you an idea. If you really produce something, you need a lot of energy. And 2 terawatt-hours is a number. That means a big lake of constant, you have to lift 400 meters higher. The idea is that you make more, and in a flexible way, you use it for valorizing chemistry. Everybody thinks about fuel, and now we work with lignins. And if we look at that, then you will see the cost for lignins are already significant. If we can make a business case of that, I don't know. The important thing is, if you go to commodities or fine chemicals, it's already reality. What are the reasons for that? One reason is the selectivity. If you look at the selectivity, if you make fuel, you don't care about mixtures. It might be even beneficial to incinerate mixtures. But if you go to commodities, polymer precursors, or even fine chemicals, it has to be really pure. Otherwise, you don't meet the market. There's no way to bring it to the market. And most things, usually organic chemists, and especially chemists in a laboratory, forget is the downstream processing. This kills 90% of the processes to come into translation. Bernd is already smiling. This is the reason. And it also is a driving force which kind of these processes will pay off if you try to electrify them. Okay, coming back to lignin, what we started many years ago, can we do this in a less brutal way, mild way? And we found a way that they can electrolyze that at relatively mild conditions. It was on nickel electrodes. Under caustic conditions, you form nickel oxide hydroxide, which is an electrocatalyst, and then you oxidize the lignin particles, and they liberate over time vanillin. The yields were at that time not very high, if you see there. It's around 1%, and you see the nickel one, the cobalt ones were very well performing, even better one than the nickel-based alloys, and there were some other alloys, but the cobalt ones really were suffering from corrosion. And therefore, only nickel worked for a good way. And the point here is definitely that you can use here the planar electrodes, which is limited in the surface. Then you go to the nickel foam, which was much better. And it turned out you can go to high current densities, or relatively high current densities, and it still works in a very good way. To increase the yield, the biggest parameter was for us then the temperature. And if you go there to higher temperature, it immediately indicated you have to go much higher than 100 degrees. And that's the one autoclave also Niclas introduced this morning. This allows us to do the electrolysis at higher temperature. To do so, then you come to a Kraft Lignin, then you break the wall of 3 weight percent. You have all the time the small sister acetovanillone on that. That's the side component. But it was relative selective. And the question is, if you go to 160 degrees, is this the end? Because the problem is you oxidize the lignin, but you can also over-oxidize the desired compound. It's a kind of riding the cannonball. Going back to the electrodes, we had a look, is the surface of the electrode very important or not? We used the foams, a planar nickel, but also a nanostructured nickel version by laser. And it turned out it makes no difference because at 160 degrees, the kinetics are so fast that the surface pattern plays no role anymore. With optimization, with different lignin versions, we could show it's possible to go even to 4 weight percent. And the question is, how are behaving different commercial Kraft lignins? And we looked at that, and you see it depends a little bit on the source of the lignin. On the right side, you see the percentage, how much of the potential available vanillin was obtained. But you see, you're around a little bit like 4 weight percent, but that's it. The problem is you kill afterwards your desired compound. The problem is we have now caustic soda in there. That's the most expensive chemical we add to this whole system. How can we do a workup without neutralization? Coming back to the downstream processing. And then the idea was, is an adsorption method possible that we just take it out and we can use the electrolyte for something else? Or even if we don't neutralize it, we can push it back into the system in the pulping factory. And the idea behind that was, because in my previous life I was a supermarket chemist, that you use just an ion exchange resin, and then you see the deprotonated vanillin, the vanillate goes onto the surface, and it sticks there. You cannot rinse it off by caustic soda. I have to explain it in a second. If you just take which is on the resin, you acidify that, then you can liberate it. And the big important point is it's a resin. That means the bigger lignin particles, the bigger broken parts are not going onto the system. Why does it work at really high alkaline systems? The reason of that is that you have a lipophilic backbone. And the lipophilic backbone allows you that it's not only the coulombic interaction, if there's more ionic interactions, it squeezes together and it sticks there. You can use the most simple one, which you find in the water filters. This one is doing the job quite well. And the important thing is, can we do this directly maybe on black liquor? Because if you look at black liquor, you have there already guaiacol, vanillin, and acetovanillone in there. And it even works there. That means you can directly use from the black liquor without degradation, get these compounds out of the system. How well does it work? You do that. We used black liquor from the Mercer group in Stendal. And it turned out that we found not only guaiacol, vanillin, and acetovanillone, but also, you see the purple one, and something which is in a very tiny amount there, but fits perfectly on the resin, and then you get a compound out of it which is still green, which you can cut in 2 pieces of vanillin afterwards if you want to do this, or use it for other applications. You can even use the system to deplete the black liquor, oxidize it electrochemically, and then once more pump it over the resin, and then you get even more out of it. That's the way if you work in the in-cell version. But you see, the problem is you electrolyze it and you kill your compound, the desired compound. There's a certain concentration you cannot exceed. Therefore, we have to avoid to electrolyze the whole mixture. That means we do something which is called XL. That means not only on the left side that everything happens in one container, we just make a reagent and we separate off the hydrogen, which is now a worthy product. And then we get this one here, we add it to the mixture. It's nothing we invented. The production of bleach is exactly this way. The first example I want to show you is that we used the peroxide dicarbonate, which was introduced this morning already. And we went to a higher concentration. This is a modified Condias cell here. And then you do it at lower temperature. You add it to the system. And now the important point is, which is coming now in several examples, you oxidize the lignin particle. The oxidizer is gone, and then afterwards you liberate your compound, but since the oxidizer is gone, you can achieve higher concentrations of the desired compound. You see, if this works, in the laboratory we could get more than 6 weight%, and even on the scale up with our colleagues in Trondheim at SINTEF, it was possible to go even to higher concentrations or higher yields. And the important point is it works on several commercially available systems. These are only commercially available lignins. And then you see this mostly Kraft lignin, and it depends a little bit on the source, but you can get to significant higher yields. This is the crude GC. You have the internal standard, that's the blue one, and the other one, you see some vanillic acid. There's still some over-oxidation. You have to put it in a little bit more specific way, but you can get a really interesting mixture which could be easily separated off. And people from Beauregard, for example, know or have described well how to separate these compounds. If you use another high-performance oxidizer like periodate, then you get directly iodovanillin. This is the only product you can detect in the low molecular range. And the important point is it's due to the heavy atom, you get, of course, a quite good yield out of it. And the important thing is it's an important building block for many applications. Playing around with other oxidizers like ferrate, and I could not resist to put this cover page here because it's like the Thor's hammer. And then you get vanillic acid. This was the only product. And when we did this, we published that, and then some of my coworkers said, oh, maybe let's make some, to make the ferrate, it's very, it's a lot of work. Let's just leave it away. Just you look for the high caustic conditions. And it turned out it's even better. And when we started that, it turned out with 50% of caustic hydroxide, caustic potassium, then you end up with a system which is extremely selective, and you end up with around 10 weight% of vanillic acid. And if you drive the conditions a little bit further, you can even demethylate the vanillic acid to protocarylic acid. And therefore, this is an interesting system. The elimination happens in a different position. Why does it happen? Because you have so many potassium ions in there which block the other ones, and then you can do the elimination. And the important point is the first step is an oxidative treatment, but this happens at the very caustic conditions, and it's known to literature, by the way. And then you can go further, and if you treat it at a higher temperature, you even demethylate the final product. And the really fascinating stuff is you can use this for Kraft lignin, you can use this even for the lignosulfonate, for a variety of commercially available lignin sources. And here you can reuse the electrolyte directly. You just pump it over the resin and use it once more at a new lignin to that, heat it up, and once more. And by the way, you can get a lot out of the system. And this is a di-anion under these conditions and fits well to the surface or in the pockets of the resin. With this idea in the hand, it was very logic. Let's go back to the vanillin. And indeed, if you do so, you oxidize the lignosulfonate. You can go roughly to 10 weight% of vanillin out of it. But it's important that you separate timely and spatially the oxidation from the liberation event. And by this way, you come in a competitive concentration, which can be even used and maybe substitute some current processes. I told you a little bit what we can do with lignin. Most likely in fuels, it's a little bit more difficult. But the important thing is we can break it down to interesting products selectively. And we can take out the important compounds with the resin and we have a way that the stuff which is left over goes back into the pulping factory, because we don't have to neutralize everything, because the process chemicals are valuable and we don't want to waste them. I did nothing of that, maybe creating some crazy ideas, but I'm really privileged to have a fantastic group, and of course also our money providers. I'm very thankful to my collaborators and all the discussions which are in there. Of course, there's a commercial break. There will be next year a big conference in Mainz. If you're inspired to have more electrochemistry, there will be one here, and before the big meeting, there will be a pre-meeting in Mülheim as well on electrosynthesis. And therefore, I'm happy to take some questions, and nobody slept away. Thanks.
Thank you, Sigi.
I made some time good, okay?
Any questions? Please.
The absorption, you have maybe 4 different aromatic compounds you could get out of it. How do you think it happens that you only get those 4 and not also other phenols?
In black liquor, the one from Stendhal, Mercer, there are no other phenols in there. These are the ones you could extract. You find in the dimeric species much more, but the only one which we find in there is the stilbene, which fits onto their resin. All the other ones are staying outside, but on the low molecular weight, you only have these 3 there. Okay. If you would have maybe benzaldehyde, it would maybe not stick on it because you don't have the anion. Yeah. But it's not in there. I fulfilled my message as a commercial break. Yeah, yep. Thanks. I'm one of the organizers there.
Do you have any other questions? If not, then let's move on. Thank you, Sigi. And now we will hear the refinery perspective by Seda Karahan and then Yannick Mathieu. Seda is working at Tüpraş, the Turkish petroleum, how's it called, corporation, a major producer of fuels and chemicals, and looking into different routes of producing biofuels. And Yannick Mathieu, he is a researcher at ITQ, the Spanish Catalysis Institute, one can say. And when Seda is done, then we will just quickly switch the presentation modes. Okay, Seda.
Thank you. Hi everyone, I'm Seda Karahan from Turkish Petroleum Refineries, and I am the product owner of the renewable fuels at R&D Center. And today I will share my slot with our project partner Yannick Mathieu from CISIC ITQ, and we will try to give you some overview about challenges and the opportunities for the refineries. At the beginning, I would like to give you a brief introduction about Tüpraş. Tüpraş is a refining company producing the energy of Turkey for more than 70 years. And today, together with 6,000 employees in 4 refineries and headquartered in Istanbul, we are the largest enterprise of our country. After investments and privatization, today we have 30 million tons of crude oil processing capacity. And for the transportation of the oil through pipelines, we have also some maritime logistics and some railway logistics subsidiaries for those, Körfez Ulaştırma and Ditaş. And OPET is our associate for the distribution of value-added products. In 2021, with the Paris Agreement signed by Turkey and the announcements to being net zero in 2053, Tüpraş initiated its transformation plan by taking steps regarding changing demands in transportation and energy sector. Mainly in 4 areas we are working: biofuels, zero carbon electricity, clean hydrogen and sustainable refining. And as the first phase of the investments of biofuels, especially sustainable aviation fuel, we signed a licensing agreement with Honeywell UOP for HEFA technology, and the estimated capacity for that plant will be 400,000 tons of waste vegetable oil and fat. And we are also trying to increase our capacity after 2035 by developing some technologies together with our partners in European funded projects at R&D center. At R&D we have 60 employees with the majority of women researchers, and EBIO was our first Horizon funded project in the field of biofuels, and we built up on it in the last 2 years with Fuel Up and Sun Fusion projects. Here, my colleague John has already given a scientific talk yesterday on our efforts in EBIO project, but here I would like to emphasize why it is so important to produce sustainable aviation fuels by looking at the emissions of the transportation sector. In total, it covers the 16% of the global GHG emissions, and aviation takes part by 2% for now, and according to the European Commission, by the middle of this century, demand for flying will increase so much that it will be more than 3 times compared to 2005 levels. Also, the reduction effect of the COVID-19 pandemic has already been covered by 80%, and there must be some precautions to stabilize them at today's level. These are the precautions are in mainly 3 fields. These are operational improvements and aircraft technologies, and without green fuels it is impossible to achieve this stabilization. Of course, there are some other options other than sustainable aviation fuel, like hybrid electric and hydrogen for the decarbonization of aviation, but they are, by the current state of art, they are very limited to commuter and regional jets due to their low volumetric densities, and that is to say a plane would need more than 50 kilograms of batteries to replace only 1 kilogram of fossil jet fuel for a 1,000 kilometer flight. Although energy density of hydrogen is higher than traditional fuels, its liquefaction is required for safety, storage and distribution purposes. On the other hand, sustainable aviation fuel, which is a kind of liquid fuel which is chemically and physically compatible with fossil fuels, it is the most promising way for medium and long range flights, and these are the flights that already covering the greater than 70% of the jet fuel consumption. Also, there are some improvements addressing the usage of advanced biofuels, advanced feedstocks for sustainable aviation purposes. In the last version of the Renewable Energy Directive, which has entered in force in the last year, by the new directive, the renewable energy use target in transportation increased from 14% to 29%, and while in the former versions they were only covering the road and rail transportation, now it is extended to all transportation sectors. And also Part A mandate is defined for the use of non-food biogenic feedstocks, and it is actually, it was there, but it is increased from 3.5% to 5.5%, including the renewables from non-biological origins like hydrogen and the e-fuels by a sub-mandate of 1%. Also, Refuel EU initiative aims to reach a 2% blend starting from next year, and year by year it is targeted to reach a 70% blend in 2050. While target sounds very ambitious, current SAF capacity of EU and UK is less than 1% of total aviation consumption, and starting from next year, EU needs 1 million tons of sustainable aviation fuel. So far, 8 standalone and 2 co-processing pathways for SAF production have been certified by ASTM. Although the availability of the biomass and municipal solid waste is high and they can be converted either by gasification followed by fish electrodes or alcohol to jet route after fermentation, technology readiness level is not as mature as HEFA. Pyrolysis is a promising technology that has to receive the ASTM approval. PTL is also advantages with unlimited source of carbon, but also you need green hydrogen, and you should reduce the prices for for carbon capture and the green hydrogen production. According to the Sky Energy Outlook, with to-date announcements in Europe, the hydroprocessing HEFA technology will reach a saturation in 2027 due to the limited feedstocks. By 2030s, alcohol to jet will only account for very little portion in the SAF production, and ESAF seems to take part in following years if everything goes well with the final investment decisions. For 2030s, the picture says that EU, yes, may reach over its SAF mandate, but obviously from that year forward, alternative routes must be added. Here, let's have a look at how these pyrolysis liquids match the needs of the refineries. For the maximization of the liquid crude, fast pyrolysis and the catalytic pyrolysis are promising to manage the chemistry. Hydrothermal liquefaction is a related process, differing from pyrolysis with the capability of using directly wet biomass. Pyrolysis produces liquid intermediates that can be converted into hydrocarbons as a drop-in replacements in fossil fuels, theoretically in fluid catalytic cracking or hydroprocessing in refineries. But we have still some technical challenges to that. Although we call them as biocrude, it is vastly different from petroleum crude, and direct pyrolysis liquids needs to be upgraded to take place in refineries. We have talked very much about their compositions and properties. They are acidic, corrosive, they should be handled different than petroleum crude. There is a lot of oxygen making them unstable, and in refineries we don't use the oxygen. In petroleum crude the oxygen is less than 1%. Therefore the oxygen or the instability causes some coke formations and the activation of catalysts. Therefore prior to process in refineries, you should struggle for oxygen removal. But in each case, for removing oxygen, you are losing some oil yield. Also, even though you don't want to lose carbon, you do in reality to some extent. Therefore, co-processing has recently received attention due to its potential to provide low-carbon renewable fuels at economically competitive prices with already existing transport and storage infrastructure. In refineries, pyrolysis liquids can be processed either together with vacuum gas oil, either in FCCs or hydrocrackers, or at milder conditions at diesel hydrotreating units. Also, if pyrolysis liquids were miscible with straight-run kerosene hydrotreating units can be used for these purposes, as it is most common for co-processing of waste vegetable oils. At Tüpraş R&D Center, we have these lab scale and pilot scale plants, and we are working in EBIO project with these plants. And I will not go through that much of detail, but on this slide I would like to just summarize what we are monitoring and targeting in converting biocrudes to biofuels. This dark colored liquid is the mixture of stabilized oxygenated pyrolysis oil with light cycle oil, which is a heavy product of the FCC unit, and it is rich in aromatics. And thanks to this aromaticity, it dissolves well these pyrolysis liquids. And light cycle oils is something that we don't want actually to treat in our diesel hydrotreating units, because as the aromaticity increases, it deteriorates the cetan index of the diesel fuel. But it is something good for the jet fuels, because in jet fuel for the seal swelling in fuel systems, it is something good and required for jet fuels, and there is a limitation, minimum 8, maximum 25 volume% aromaticity should be there in the jet fuel. And upon hydrotreating and removal of the sulfur, nitrogen, oxygen, some carbon-carbon bond cleavage or aromatic saturations, we can decrease this aromaticity in light cycle oil together with SDPO to 20 volume. Percent. This is in the range of the jet fuel specification. And also in co-processing, it is something that we need to track in the product, which is where this biogenic carbon goes. These studies is still running in Turkey at our pilot system. And at the end of these studies, we will also conduct an 14 carbon radioactive carbon analysis for the detection of this biogenic carbon. I will not that much about this slide. You know everything very well. Here I would like to indicate that the most short-term solution is the co-processing, and because for standalone operation, when you look at the capacities of the pyrolysis plants, they are very small compared to refinery units, and you should upgrade it, and we have to find a much more cost-competitive solutions for their upgrading for standalone operations. I would like to thank the organizing committee and all our partners from EBIO project. I can leave the stage to Yanni, and I will be glad to answer your questions at the end.
So thank you very much. Can you hear me well? Thank you, Seda, for your good presentation. So my name is Yannick Mathieu. I'm coming from ITQ. So ITQ is a joint research center from the Polytechnic University of Valencia and from the National Research Council of Spain. We are located in Valencia, so in Spain here, and we are also a public research center with something like 40 researchers, a lot of PhD students, around 50 PhD students, postdoc position, and we have also the support of a huge number of persons from maintenance and lab assistant and so on. So ITQ work mainly in different topics. The pillars are from energy, sustainability, health, and water treatment. I will now give you more information about this, just to have a whole picture of the different activity we can have, and I will go directly to the adaptation of refiners to reach decarbonization for the production of synthetic fuels from lignocellulosic biomass. So mainly we speak a lot about the opportunity we have to have a solid biomass and to produce liquid biomass from the solid one, applying different processes, mainly thermochemical processes like pyrolysis, hydrothermal liquefaction, or mainly to obtain a biocrude which can be pumped and which can be managed by refiners in different processes to obtain on-spec biofuels. Biocarburants, yes, biofuels. The main problem of these biocrudes is they are very different and not common for refiners because they are very different characteristics. The first one is the low hydrogen to carbon atomic ratio. So here normally pyrolysis oil or biocrude from HTL lakes of hydrogen. So it's a problem because the product we want to have, like gasoline, diesel, and sustainable aviation fuels, have to have a much higher hydrogen to carbon content. So here we have to apply process, removing carbon, but we want to avoid this, or including hydrogen inside, like hydrotreatment, hydrocracking, and so on. So this is the point. At the same time, I will not repeat the same things that we already said. We have some issues about acidity, blending issue with standard fossil fuels, derivatives, crudes. And we have a lot of heteroatoms, mainly oxygen, but which have mainly oxygen, which have to be removed to obtain final on-spec fuels. So here, to have an idea, I put some images, analysis by GC. Here you have some typical products obtained from FCC cracking. And here you can see the different hydrocarbon products we obtain, and which are inside the gasoline, diesel, and aviation fuels. And here I put the picture of the initial pyrolysis liquids. So they are very, very different. So from this, we have to obtain this kind of products. Pure hydrocarbons, mainly paraffins, olefins, and aromatics. And at the beginning, we have only oxygenated compounds, mainly phenol derivatives, carboxylic acids, and so on. So from the previous talk, you already know that the idea of the EBIO is to apply some electrochemical upgrading, allowing to already do some upgrading to do some depolymerization of some lignin high molecular weight compounds, and also to remove already a lot of oxygenated compounds, leading to the production of biocrudes much more easily to be co-processed in hydrotreatment or catalytic cracking in this case. So here you can see the kind of product we can obtain applying this kind of upgrading. So with two different level of upgrading, and you can see that we are already able to obtain some pure hydrocarbons coming from the pyrolysis liquids, including some saturated and also some aromatic compounds, and we are able to remove efficiently carboxylic acids and also all the high polymer weight products, and also some alcohols, aldehydes, and so on. And partly we can remove also some phenolic compounds, so making it much more easier to co-process in FCC, for instance. So here I put some information about the physical characteristics of this different pyrolysis oil before and after upgrading. As Robbie said this morning, one important point here, because during FCC we are working with a solid catalyst, acid catalyst, which is very dependent of the coke production during the co-processing. So we want to limit as possible the carbon residue of the pyrolysis oil will be co-processed. So you can see that applying different degrees of upgrading, we are able to limit the content of carbon residue for something like 20 at the beginning to less than 1% in the case of the higher upgrading pyrolysis oil. And removing at the same time a lot of heteroatoms and keeping as high as possible the carbon contents on the hydrogen to carbon atomic ratio, which will help a lot to do some co-processing in FCC. So we have different options here to do the integration in a refinery. We can take the upgrading pyrolysis oil as a whole and to put it directly in the FCC, or we can also do some previous fractionation, taking the light fraction and send it to hydrotreatment, and the heavy fraction and send it to FCC to improve the yield of the interested fuels such as gasoline, kerosene, and diesel. I will show you some results we obtained, but I will go fast because yesterday my colleague Ferran already showed some results about it. So what we did at the laboratory, we use an in-house developed reactor, which is named a microdonor, which is a transported catalyst bed reactor, allowing to mimic very well the FCC at laboratory scales. So this reactor allows to work under very similar conditions than the one used in an industrial FCC unit. So we did some tests, changing the incorporation level of the different pyrolysis liquid, upgraded to a pyrolysis liquid, and using as reference an ECAT catalyst and also a vacuum gasol, which is typically cracked in FCC units. So what we show, I will not go in details here, but what we show is we saw clearly an impact of the upgrading we can do on this pyrolysis liquid, allowing to limit the fast desactivation of the catalyst, limiting so the decrease of the catalytic activity, and also having a beneficial impact over the different product selectivity, for instance, gasoline, kerosene, and also diesel producing during this process. We show also that there is a clear positive impact of the initial upgrading of the biocrude over the overall elimination of oxygen during the co-processing, being much easier to co-process a pyrolysis oil which has already been largely upgrading using, for instance, electrochemical upgrading. Here I put you some example of product we can obtain during the co-processing. Here it's at 50% of incorporation, and you can see at the beginning we have a lot of phenolic, acidic, and alcohols, linear alcohols inside the initial biocrude. We are able to have almost complete elimination of this kind of oxygenating during the co-processing, leading to very results and fuels. We are not fully on spec, but quite close to the necessary specification, and we can do some blending with standard gasoline and so on to obtain on-spec fuels. So here, just to show you also that we can have a good idea of the exact composition and the exact influence of the co-processing over the composition of the gasoline in terms of content of aromatics, content of olefins, of oxygenating, and so on. And it will help us to know exactly the composition of the influence and how much we can blend of the different biocrudes to obtain on-spec fuels at the end. So thank you very much.
Do we have questions to Seda and Yannick?
Mentioned that cyclic hydrocarbons is good for jet fuel and renewable cyclic hydrocarbons. Is someone working with jet fuel not going to happen.
Cyclic hydrocarbons is okay, is better for the freezing point cold flow properties of the jet fuels, and also if it is isonaphthenic components, it is much more better. But in this kind, I don't know in the industry whether there is a company working specially for those. But in our projects, we are also struggling for it. Maybe Robbie want to say something.
Yeah, that's a very interesting question, because the cyclohexane, from the last couple of months, I realized that whatever kind of biomass you apply, whatever kind of process you apply, you'll end up with a product spectrum in your kerosene range, not your kerosene range, where you have around 60, 70, 80% of cyclohexanes. Cyclohexanes are a very interesting material for engines, also aviation fuel, but they are not used to it. So there's a link, there's a challenge there. So when you go through HTL, through IH2, through pyrolysis, through catalytic pyrolysis, and then hydrotreating, you all end up with a cyclic alkanes. Especially the Institute of DLR is now busy in that field, trying to set the first step towards standardization. I know that also Sky Energy is doing some work on this field, but it's a very complicated story if you start this standardization technique. So I would like to get far away from the details there. The overall picture is whatever you do with biomass, whatever process you make, the kerosene fraction contains a lot of cycloalkanes, which is amazing. Even if you start with lignin.
I'm a bit curious on the solubility. You said 25% in diesel. Is that do you have any way of evaluating that? For example, if you look in a microscope, you might see small drops.
No, what we do, it's very simple test. We do mix, we let it during one night and see if we have some separation. Okay. And we use DSL because the color difference is high, so it's easier to see if there is some separation. But what we do normally, it's to do a blend. If you have some kind of emulsion, you see it directly because it's like, yes, you see like a mayonnaise. Yeah, it's completely different. And what we do is to let it overnight and to see if you see some separation.
So to bother you again, also a very interesting question, because that's also something we are busy with, and not only we, but also Tupras, I think. There's a very nice machine called the TurbiScan. And well, we are trying to get some feeling about what this TurbiScan is doing. But what it basically does, it is, according to the company, it is 100 or 200 times better than visually. What it does, it scatters. It's using light, and you measure the backscattering and the transparency over a distance of 25 microns in a small vial, and it goes up and down, and you have 25 seconds for the complete vial to analyze, and you from the data you will get a lot of information on stability, phase separation. TurbiScan.
Any other questions? If not, then I don't want to keep you away from the Swedish meatballs.
No, we have salmon today.
Thank you for attending this session. Thank you all the presenters for sharing their views and their results. If you're interested, have a look at the website of EBIO. We have a couple of webinars there that you can watch that again focus on electrochemistry, on pyrolysis, on co-processing. And there will also be a couple of publications, reports, and so on published. Thank you and good lunch.
Nee, I was never